let's look at the research strategies that allowed this discovery, that is, of superconductivity. And I don't know how many Nobel Prizes superconductivity has resulted in, but a number. First of all, use the best instrumentation available, and I suppose we're really talking now about the refrigeration device, which literally allowed chameleonists to look at nature in a new and different realm. Don't reinvent, borrow technologies you can. Dewar had invented the Dewar flask in order to liquefy hydrogen, and chameleonists was very happy to copy that technology. Look into an unexplored region of the landscape. In this case, we're really talking about looking at the properties of materials at temperatures very close to absolute zero. Chameleonis was literally the first person to do that. And this is really an important one. Failure might be an invitation to try something new. So after liquefying helium, Chameleonis spent 2 years pumping on the liquid helium to try to find that it would solidify. And eventually he gave up and looked around for something else that he could do with this wonderful system that he had. And now I put in red, unfortunately this LCD projector doesn't project red very well. And you notice that the Honeywell was almost impossible to see. Now, I had done it in blue, but Mr. Kelly here, Reed said that it was supposed to be in red because that's the way the motto of the company is anyway. So this is, be aware of subtle behavior, don't dismiss it. Now this is what I'm really referring to here is that as he pumped on the liquid helium, he noticed at a particular temperature of about 2 Kelvin, a little above 2 Kelvin, that the helium stopped boiling. And he wrote that actually in his lab book, but he never pursued what was going on there. That, of course, would have been allowed him to be the discoverer of superfluidity, which was actually was no particular person that absolutely discovered that. But I think the person that came closest was Peter Kapitsa, who in the bleak winter of 1937 in Moscow measured the viscosity of liquid helium, and he was using a technique that made him sensitive to the superfluid component, and he found that the viscosity was less than 1/1000th of a poise. So this is a picture of Peter Kapitsa. I actually met him the first time he was allowed to come out of Russia at Cornell University. Interesting fellow for sure. But he did not share the Nobel Prize for his discovery, which was done in 1937, until 1978. I don't know why it took so long, but at least he was still alive when they gave him the Nobel Prize. But it's interesting that he shared the Nobel Prize with two people whose research had absolutely nothing to do with condensed matter physics at all. So they were my good friends, Arno Penzias and Robert Wilson. So when I was at Bell Laboratories, Arno Penzias was vice president of research. So he was my boss's boss's boss, I suppose, at Bell Laboratories. And Arno Penzias had been hired by Bell Laboratories. His background's actually in electrical engineering. And he was given a microwave receiver that AT&T had used in early experiments on satellite telecommunications. Looking at this relatively young audience, probably few of you remember the Echo satellite. Does anyone remember the Echo satellite? No. Okay. It was a mylar, aluminized mylar balloon that inflated in orbit. It didn't inflate right. And then the other one was the Telstar satellite system. And when they were done with those experiments, AT&T gave the receiver to Penzias, who then had hired Robert Wilson, and they were to use this to make the first absolute radio noise measurements that had ever been made. So this is that wonderful piece of apparatus, and you can tell by looking at this handsome piece of equipment that this was very high tech. So this is a horn antenna, which has the advantage that it has no lobes of sensitivity that would include signals coming from terrestrial sources. So they pointed this up into a point in the sky where there were known to be no radio sources, just to measure the noise level of the receiver. Actually, the key to this thing wasn't this horn antenna, but inside this shed was a traveling wave tube maser amplifier using a doped ruby rod, which had gave this system an integrated noise temperature of about 19.2 Kelvin. Actually, you might ask the question, why was AT&T interested in looking at radio waves coming from outer space? Well, it's really because of this person here that you can barely see. This is Karl Jansky. Karl Jansky was an electrical engineer working for AT&T back in the early 30s when AT&T was interested in seeing if they could carry telephone conversations over radio waves. But there was a lot of excess noise that they didn't understand, so they asked Karl Jansky to find out where that noise was coming from. And Karl Jansky created this elegant-looking directional antenna, and he just looked at the noise as a function of the time of the day, and he did this for a long time. And what he found was the period, this noise tended to oscillate in time, and the period of the noise was not 24 hours, but roughly 24 hours minus 4 minutes. And so for people that study astrophysics or even just astronomy, you know that suggests it's behaving according to a sidereal clock, a clock that is outside our solar system. And so when Karl Jansky convinced the people at AT&T that this noise was coming from someplace else and that he wanted to find out where, AT&T reassigned him to a different project. They said that if the noise is not coming from the Earth, we don't have any control over it, so get back to work. And it turned out there was a guy named Grote Reber who actually was a ham radio operator, figured out that this noise was coming from clouds in the Milky Way galaxy. So the reason, now you might wonder why this antenna was so good, and it really had to do with traveling wave tube maser amplifier. It was Charles Townes, shown here, who invented the maser back in, what year was it, 1954. This is Charles Townes. Jim Gordon actually went to Bell Laboratories. I think the work was done at Columbia University, and then Jim Gordon went to Bell Labs. And in fact, when I was at Bell Labs, Jim Gordon was still there. So this is the maser, but this technology would not have worked. It was actually Nicholas Bloombergen at Harvard that invented the doped ruby rod maser, which was the useful, provided useful low noise amplifier that was necessary for this work. So here's their first data. And back in the old days, all the data came out on a strip chart recorder. There was a pen that would go back and forth that indicated a voltage, and then the paper moved underneath that pen, and so you got things that looked like this. So here you can see this says antenna, and it says some angles. So this was, they were looking at the noise coming in from outer space in a place where there's supposed to be nothing. And then they had a microwave switch on this thing. They could then, to make absolute radio noise measurements, they compared this with the noise being radiated by a black body at a temperature of 4.2 Kelvin, liquid helium temperature. And they concluded in the end that, in fact, there was a noise coming down from the heavens, roughly about 3.3 Kelvin, that they could not explain. And of course, this is the cosmic microwave background radiation resulting from the things that happened in the early universe roughly 400,000 years after the Big Bang. But anyway, I'm getting ahead of myself. They looked at this and thought this was extra noise that they shouldn't be there, so they really understood their apparatus, but they decided they would go back and look inside their antenna. And what they found was the pigeons had been roosting inside the antenna. And so they batted down the pigeon nests and mopped up the pigeon droppings, and I think a few copper plates had to be resoldered in place. but nothing that they could do would allow this noise to go away.